chart of just some metabolic pathways is almost as tall as me. But all of this molecule making and breaking is taking place inside of tiny little cells inside my body and your body, and it's so cool. So let's talk about it.
Today I'm going meta and talking about metabolism. So metabolism is just a fancy umbrella term for the making and breaking of biological molecules. So this term encompasses anabolism, which is molecule making, and you can remember this as thinking of like professional athletes abusing anabolic steroids to bulk up their muscles. And then there's catabolism, which is molecule breaking. So think of like your cat destroying your couch. So catabolism is often used to generate energy or to get smaller reusable parts. Kind of like if you had a big built Lego set and you broke it down, but you left some of the pieces together because those pieces in those together shapes could still be useful for another structure that you're building. So, for instance, you can break down a big sugar molecule and use it to make another sugar molecule of a different type, or to make generate energy. And the important thing to remember is that there's a bunch of pathways, and they're all interconnected like a web. Like, we often talk about them as these linear pathways, but really most of the steps are reversible, and the pathways can go either direction. So you can make or break with the same pathway, and the pathways are all interconnected. So, for instance, one that we're going to talk about a lot, glycolysis, which is the breakdown of glucose or blood sugar, you can have other sugars enter the pathway at different points and still get processed the same way after that point. And if there are steps in a pathway that are quote-unquote irreversible, basically that just means they're so energetically unfavorable to go the opposite direction that they're just not gonna, unless there's like some major change or whatever. But there are ways that the pathways can bypass those irreversible steps, and then you could use the rest of the pathway. So a lot of the metabolism, like which way the pathway goes, depends upon regulatory factors as well as the concentrations of the various things. So we're going to talk a little more about catabolism, so molecule breaking. And this is often what people are referring to when they say metabolism, even if they don't say catabolism. That's often like assumed that you're talking about breaking down molecules. And often this breakdown is to get energy. And the way that the body stores energy is in a molecule called ATP. And I was always super confused when teachers would talk about like ATP storing energy. So I just want to explain what we mean by this. So ATP stands for adenosine triphosphate. And it's actually an RNA letter, so it's a nucleotide, triphosphate. And basically, a phosphate is a phosphorus atom surrounded by oxygen atoms, and it has a negative charge. So in ATP, you have 3 of these negatively charged phosphate groups really close together, and opposite charges repel. Like charges repel, opposite charges attract. So you have these like charges close together, and I like to think of this as kind of like you're clamping a spring, like a stiff spring together. And if you let go, it's gonna like spring out. And so if you were to have like a ball or something at the end of that spring that you have clamped, then you let go, that ball would go flying across the room. So instead, instead of like making a ball fly across the room, we're gonna use that energy to do things like build molecules by putting them together, because molecules, it often takes energy to make them stay together, because molecules want to be all free and have high entropy, which is like the ability to move in different ways and stuff. So you have this ATP, and so it's like a clamp spring, and if you let it go, then you get energy. And that's going to be the core idea throughout catabolism. So where does this negative charge come from? So to get at that, we have to look at what elements are made of. So elements, it just refers to like hydrogen, carbon, nitrogen, oxygen, or whatever. If you want a full list, go to the periodic table. And so basically, elements, the smallest or like unit that is still like an element or whatever is an atom. And atoms are made up of smaller parts called subatomic particles. And so at their core in this dense central nucleus is the protons, which are positively charged, and neutrons that are neutral. And then floating around those are really, really, really tiny little negatively charged particles called electrons. And the electrons kind of whiz around in this electron cloud. We often talk about them as being located in an orbital. So in like the shell model, you'll see these shells with the electrons in different levels. And so it's not really how it is physically, but it's helpful for kind of explaining the basics of things and how things end up working out in a practical scale. So in the outer shell are what you call valence electrons. And so they're farthest away from the nucleus. And so the nucleus is where the positive charge is. And so we have that opposite charge attract thing. So the protons in the nucleus are kind of trying to rein in those electrons. And especially the electrons on the outer edge, they don't want to be reined in, and they can't really like feel the positive pull that much. So they're going to be freer to leave if they want, and join other atoms, and that's how you can get like a negative charged molecule if you have an excess of electrons compared to protons. And atoms can also share electrons. So when molecules share pairs of electrons, we call that a covalent bond. And that's how we get the intramolecular bonds, so the bonds that hold molecules together. So it's 2 electrons is a single pair, a single bond, 4 electrons, you get a double bond. Then you can also have lone pairs, which was unbonded electrons. And then if you have unbonded single electrons, we call that a radical. And then there's this thing called, if you have electrons get transferred in a reaction, we call that an oxidation or reduction reaction. So we say we have this mnemonic oil rig. So oxidation is loss of electrons and reduction is gain of electrons. And so this is going to come into play in a process called oxidative phosphorylation, which is really key to, it's the big moneymaker, energy moneymaker in catabolism. And so you're going to take a molecule such as glucose, so blood sugar, and you're going to basically oxidize the heck out of it. So you want to just like you want to take all of its electrons, and then what you're going to do is you're going to transfer those electrons to carrier molecules like NAD, and then those carrier molecules are going to take them into the mitochondria, which is a central compartments inside of your membrane-bound compartments inside of your cells where the energy making can occur. And so those electron carriers are going to take those electrons, and what they're going to do is they're going to use it to pump protons. So pump these H plus. So sorry, the naming's kind of confusing because a hydrogen only has 1 proton to begin with. So if you lose an electron, it's just a proton. So that's why we call it protons, even though we just said that protons were those positively charged parts. So for the hydrogen, it's the same thing. But so what you're going to do is you're going to use those electrons to pass them from one molecule to another to pump these electrons out of the inner part of the matrix and into this like intermembrane space. And then you get this like high concentration of protons. And what they're going to do is they're going to flow through the this ATP pump back into that central part of the mitochondria where there's a lower concentration of protons. And it's kind of like a dam. It's going to, all that that rush of protons is going to turn this molecular crank and pump out ATP. So it turns out that from cellular respiration, so from one molecule of glucose, if you take it all the way through to oxidative phosphorylation, you can get about 26 to 28 ATP molecules. And then like the ATP molecules are kind of like arcade tokens, so you can use them anywhere, no matter where their source came from. Now they're all the same. And so I hope that helped you explain catabolism.